thanks everyone for coming uh, to the last lecture in the Guerrilla Lecture series. It prematurely ended. Today for the last weeks we had a few things on like how we're building language with nice syntax, how we're making type system, and how to get search run. And for this last lecture, I thought I will share with you some ideas on how we improve on the search that we saw last time. So the search that we saw last time it's called the DPL algorithm, or conflict-driven cross learning. And today we're going to explore some ideas on how to get a notion of an optimal search, or how to speed up our search algorithms with the language tools that we did. Okay, so quick recap from last time. So when we have our knowledge base, we have our rules, and then each variable is one point in our memory. And on this memory, we formulate constraints, with which then the memory is being filled with the things that we said we have to put on here. Now then we had the unit propagation, which essentially looks to our rules and just sees how many possibilities do we have for a certain variable. Those variables that only have one possibility are filled. So if we see, we have length 1, the action doesn't fit, so we have to apply the rule. Then the list constructor is being split up, we create new variables, and all the right-hand side constraints are then being added onto our memory again. Now the cool thing about this example is that the unit propagation that we saw from last time directly solves our riddle. So in this case we want to have a list of length 1 but with a sum of 3. And so by length 0 being an axiom, there's only one thing that can be filled in here. By sum of the empty list being an axiom, there's only one thing that can be filled into the z in the end. And by add x plus 0 also being an axiom, meaning the 3 has to be equal to the x, also an axiom, and so this whole thing can be deterministically solved with the unit propagation. Okay? However, when we are dealing with general solving, we also often run into situations like these ones. So just through unit propagation, we cannot tell what to fill into our variables in here, because they're there's just like two possibilities, the problem is that when we actually build a search algorithm, at some point we have to have a clause like this one standing. So whatever we have as a source predicate or something, it needs to take this formula and then fill it up such that it actually fits into one of the actions. We just have to make deterministically how that happens. Now, one thing that looks a bit odd is that here we can see that I declared some variables as like open or bound. The reason for this one is when we are only writing predicates on top level, they cannot distinguish between open variables or closed terms, because like as soon as they reference a variable, they always reference the value of it. And so in order to build these meta predicates with which we can actually realize search, we have to do something called coding. So what's the concept of coding? Essentially, coding is a mechanism of how we can communicate with our compiler. So when we have a term, we cannot necessarily see whether this case is a variable or is being filled with something. So together with our compilers, we can make a code function that can then put the information, like the additional information, into our terms that we need, which variables are open and which one are bound. Also, like when we have a solving state, it's often that within the solving process, some variables they could have a value, but they don't have a value yet because it hasn't been deduced yet. And yeah, so something similar to the coding can be used to implement this. Yeah, so a solve function, it essentially runs on quoted terms. Just one example of how that could look like. So we have here the define k as a universal rule, and then we try to find this, and if we then merge k with this, it fits. However, as this looks a bit cumbersome, I'm not going to like specifically say when something is quoted or not. But yeah, so when you build your compilers, this is kind of what it looks like. This is where we actually want to go. So when we build like some kind of solve predicate or something, technically while we're doing the solving, there's a lot of such clauses that we produce. So like from a certain solving state onto the next solving stage, there's a lot of clauses that are kind of like a program trace or something. And as we've seen in the first lecture, we can technically use logical programming as, for example, machine learning or something. So when we do not know exactly how we want to construct our solve predicate, we can still put this trace into our knowledge base and then construct the solve function that we want to have in the end. And here's a bit more of a concrete way of how that can look like. So essentially we're searching for a specific predicate that takes transforms from one formula into another one, and we want to make sure that this one is deterministically this one is deterministic and still is viable to make a proper search algorithm. So yeah, just a few things. So we first assume that we can go from F1 to F2 by either one rule application or like a finite amount of rule applications, so that we know that F2 stays valid. So then F2 contains some clause that represented which step we actually took. Meaning that when we take some step, we at least know in F2 that which step we have taken, so that we can reason about what we actually did. The third step, maybe F1 contains. So like this maybe notion I put in here. Essentially, what this is saying is, if in F1 we already have a clause that determines which one is now the next step, which one is now the next predicate to be derived, then we also have to act accordingly. If it's not in there, we just ignore this one. Yeah, deterministic from F1 to F2. Maybe a question. So what could be like a notion of determinism for us? Okay, we will look at this one in a second. So we actually have like the problem is that the whole language that we've created until now it behaves inherently non-deterministic, but the machine that we are running it on, it operates some code deterministically, and we have to make sure that these codes stay the same. And we see it in a second. And we have to make sure that when we use this as an actual solving function, where we go from F1 to F2 repeatedly, so then from F2 to F3 and so on and so forth, that we still stay complete, meaning that if there is some goal, we eventually reach it with a step function. Okay, deterministic. This could be one notion of determinism where we can say, okay, when we go from some formula X to some formula Y, there can only exist one formula Y where we can go to. The problem is that this even can be pretty hard to find out. So this is like a question if there is only one solution, but like it can still be hard to find the solution. So what we also need to build into our compilers is the unit propagation itself as a predicate, so that we can say, okay, like when we're going step from F1 to F2, the step has to be deducible by only unit propagation. So we just go essentially either when we use the step function we already reach a goal, or we take a step and then from the next step on we reach a goal. So As long as we're using this, yeah, we reach some goal in the end. And yeah, and the cool thing is that all of these things are just normal clauses, meaning that the unit propagation clause learning that we had from last time, when we deduced these things partially, but they have a conflict. For example, it's not deterministic at some point, or we know that there's a goal that we can't reach. Then this would cause a conflict once we realize, and the clauses are being changed, meaning that when we now do the further solving, because the clause has been changed, we now act according to the change that we've deduced. Okay. One interesting observation is when we apply our solve function recursively, it's often that we have the context is like these are all the clauses for the rules and stuff. So like all the context that we need for solving. But if we apply this more often, we can see that the length of the clause that we are doing the solving on can, for example, decline. The shorter the function, the shorter the formula is that we actually do the solve on, the easier it is to find common rules of how solving works. Yes, let's look at an example. So let's assume we, for example, do not have enough space in our memory. There's a way of how to how to compress predicates. So, for example, if we have all tokens of our language just in one predicate, we can also say, well, if these are all tokens anyway, we just have this one as an axiom, so we don't need to check in our knowledge base of what something is. Something similar works when for example, not all things are here, but like, for example, only fruits in this case happen here. So we essentially compare all of those. They only share, for example, the salad token, and then the two variables that we have universally, we just have to constrain them further with how we can compress them. So that is where. So when we have these huge these huge program traces of our solver, this is how we can compress them, and we can see that, for example, when we would have to check this one if it's valid, this would be way slower than actually just checking whether this rule fits. So yeah, when we're already talking about speed, one nice thing that we can do when we have our solve predicate, we give it a program, we want to know if it has a result or not, and maybe we get some proof. Another way how to formulate this is that we can also say we just have a solve predicate that gives out the steps of the computation. So of our current step function, this one can take a program and either, if we're lucky, predict part of how many steps we're going to need on our current formula, or if we don't know, while we're doing the solving, we get more and more knowledge on how many steps we actually need in order to run our program. And if we embed this also in our solve function, essentially we can say, well, maybe there's several ways of how we can go from an in-between state to another one. The only thing that we have to now make sure is that, that we now want to make sure, is that we always go onto the next state of which we know it has, the quickest way to the goal. Meaning, the more information we gather about how far we are likely to reach a goal, or like how far we reach a goal, eventually putting this notion in would make the solver converge to the kind of fastest solution that can be operated by pure unit propagation and therefore deterministic. Okay. So that one Yeah, okay. So that one was essentially the idea that like should I complete the search chapter for what we had. So yeah, essentially the idea is that we use the from the choosing, for example, the generate clauses that we generate through the search, and put them as our search predicate back into our knowledge base, and then we're forcing the compiler when the compiler is operating our language to act according to these facts that we have gathered already, and therefore the solving algorithm can change over time and yeah, can improve speed over time. Okay, then yeah, then that is it for the Guerrilla Lectures. So that is got so short today, but yeah, thanks you all for being here, and yeah, let's have fun building our languages. Thank you.